Hello, and welcome to the fifth lesson of the Lean Six Sigma Green Belt course offered by Simplilearn. This lesson will focus on the improve phase of the DMAIC process. The improve phase comes after the analyze phase. In the analyze phase, the data was analyzed and some patterns were found to identify where the problem lies. In this lesson, we will review the improve phase to understand how to go about the improvements, their validation, etc. Let us start with the objectives of this lesson in the next screen. After completing this lesson, you will be able to describe the concepts of design of experiments, DOE, explain the uses of residuals analysis and BoxCox transformation technique, discuss the cause and effect matrix and the 5 Why tool in root cause analysis, explain the Lean and Kaizen techniques. Let us proceed to the first topic of this lesson in the following screen. In this topic, we will discuss design of experiments in detail. Let us learn about design of experiments in the following screen. Design of experiments, or DOE, consists of a series of planned and scientific experiments that test various input variables and their eventual impact on the output variable. Design of experiments can be used as a one-stop alternative for analyzing all influencing factors to arrive at a successful model. DOE is applicable where multiple input variables, known as factors, affect a single response variable. An output variable is the variable which may get affected due to multiple input variables. DOE is preferred over one factor at a time, or OFAT experiments, because it does not miss interactions. With techniques like blocking, experimental error can be eliminated. The trials should be randomized to avoid concluding that a factor is significant when the time at which it is measured or the sequence followed may have influenced the response's result. An example of blocking is highlighted in the table given on the screen. With techniques like replication, many experiments can be conducted to ensure a robust model. We will understand the concept of design experiments through an example in the upcoming screen. To understand DOE and the main effects, consider the following example. Suppose the objective of the experiment is to achieve uniform part dimensions at a particular target value to reduce variations. The inputs, X, or factors that affect the output are cycle time, mold temperature, holding pressure, holding time, and material type. The process is the molding process, and the output or the response of the experiment is the part hardness. The components of the DOE in this example will be described in the next screen. Output response, factors, levels, and interactions are the components of the DOE in the given example. Click each component to learn more. The response variable is the part hardness and is measured as a result of the experiment and is used to judge the effects of factors. Factors of this experimental setup are cycle time, mold temperature, holding pressure, holding time, and material type. Factors can be varied and are called levels. The molding temperature can be set at 600 degrees Fahrenheit or 700 degrees Fahrenheit. Plastic type can be fillers and no fillers, and the material type has two levels of nylon or acetal. Interactions refer to the degree to which factors depend on one another. Some experiments evaluate the effect of interactions. In the molding example, the interaction between cycle time and molding temperature is critical. The best level for time depends on what temperature is set. If the temperature level is higher, the cycle time may have to be decreased to achieve the same response from the experiment. Let us understand full factorial experiments through an example. Full factorial experimental design contains all combinations of all levels of all factors. This experimental design ensures no possible treatment combinations get omitted. Hence, full factorial designs are often preferred over other designs. The table shown here is for a two-way heat treatment experiment. There are two factors, oven time, X2, and the temperature, X1, at which the material is drawn out of the oven. The output, Y, of the experiment is the hardness of the material. Each of the factors has two levels. This example illustrates the concepts of main factor and interaction effects. From the table, it is clear that without repetition, the experiment will have 4 different outcomes based on the changes in levels of factors. Each experimental trial here is repeated to give a total of 8 values. Let us now analyze the mean effect. An analysis of the means helps in understanding how a change in temperature at which the material is drawn creates a difference in the average part hardness. This affects the output and is called the main effect. Analysis of means also tells how a change in oven time creates a difference in the average part hardness. This is also the main effect. Analysis of means explains how interaction between temperature and time affects the average part hardness. This is known as the interaction effect. Let us next understand the concept of main effect. For calculating the main effect, the means have to be calculated. Hence, to calculate the main effect of draw temperature, the mean of the hardness values has to be calculated. The values are populated in the corresponding columns of draw temperatures. The columns have been labeled A1 and A2. The value of the mean of A1 is 91, and of A2 is 82. Plotting the data on a graph shows that changing draw temperatures changes the average hardness. Similarly, we calculate the mean of hardness values in B1 and B2. The values are 87 and 86, which are plotted on a graph. It can be seen that changing the oven time does not affect the average hardness. Now let us understand how the interaction between temperature and time affects the average part hardness. To check how draw temperature and oven time interact, the mean values are calculated by taking the repetition response. Hence, the cell A1B1 has the mean of the values 90 and 87. The cell A2B1 has the mean of the values 84 and 87. After the mean values are calculated, they are plotted on a graph. The graph shows that to reduce interactions, low temperature and high oven time should be selected to have the desired output of high hardness, also called Brunel hardness. If low hardness is the desired output, the experimental setup should have high draw temperature and high oven time. The ideal case is represented by the parallel lines, which give the desired output based on the main effect without being affected by the interaction between the factors. The parallel lines are shown as a dotted line. The mean of the factors are also calculated and shown in the small table. In this, we will introduce the concept of runs in design of experiments. The numbers of experiments in a DOE setting is known as runs. A full factorial experiment without replication on 5 factors and 2 levels is 2 raised to the power of 5, which equals 32 runs. A full factorial experiment with 1 replication on 5 factors and 2 levels is 32 plus 32, which equals 64 runs. A half fractional factorial experiment without replication on 5 factors and 2 levels is 2 raised to the power of 5 minus 1, which equals 16 runs. A half factorial experiment with 1 replication on 5 factors and 2 levels is 16 plus 16, which equals 32 runs. The number of combinations can be determined using the formula L to the power of F, where L is the number of levels and F is the number of factors. Half fractional factorial is calculated using the formula L to the power F minus 1. At 3 levels, 5 factors full factorial experiment would amount to 243 trials, and half factorial experiments would require 81 trials. The difference between full factorial and half fractional factorial experiments can be seen from the number of runs. Let us proceed to the next topic of this lesson in the following screen. In this topic, we will discuss root cause analysis in detail. We will learn about residuals analysis in the following screen. While performing the regression analysis of a linear or nonlinear model, you will get a model with the predicted values. Some of the data might fit within that model, whereas others may be scattered across. The model equation predicts one value for y at level x. However, the actual value for y observed at that level of x is different from the predicted value. This difference between the observed value of the dependent variable y and the predicted value is called residual. The formula to calculate residual is observed value minus predicted value. Residuals are considered to be errors, and each data point has one residual. You can validate the assumptions on random errors as they are independent, exhibit normal distribution, have a constant variance sigma square for all the settings of the independent variables, and finally, have a mean as 0. In the next slide, we will continue to discuss residuals analysis. As discussed in the previous screen, while performing any regression analysis, you will observe that not all the data fits into the linear model, as the linear regression model is not always appropriate for the data. Therefore, you should assess the appropriateness of the model by defining residuals and examining the residual plots. If all assumptions are satisfied, the residuals should randomly vary around 0, and the spread of the residuals should be the same throughout the plot. That is, no systematic patterns are observed. Remember, in residuals analysis, both the sum and the mean of the residuals are 0. Residuals and diagnostic statistics allow you to identify patterns that either poorly fit in the model with a strong influence on the estimated parameters or have a high leverage. It is helpful to interpret these diagnostics together to understand any potential problems with the model. In the next screen, we will learn about data transformation using the BoxCox method. The available data must be transformed when it does not exhibit the normal distribution. Box and Cox, in the year 1964, developed a procedure for estimating the best transformation to normality within the family of power transformation. It works by taking the current y data and raising it to the power known as lambda. The formula for transformation of y is represented as y asterisk equals y to the power lambda minus 1, the whole divided by lambda. This formula is used where the value of lambda is not 0. If the value of lambda is 0, you can use natural logarithm to transform y. The family of power transformations can be used for the following: for converting a data set so that parametric statistics can be used. Here, lambda is a parameter to be defined from the data. For any continuous data greater than 0, this will not work when the values are less than or equal to 0, transforming specs. Note that the use of the transformation does not guarantee normality. In the next screen, we will continue the discussion on data transformation using Box and Cox. The table on the screen shows how the data can be transformed using lambda. The first column lists down values of lambda, and the second column shows the transformed value. If the value of lambda is -2, it becomes y to the power -2 after the transformation, which is 1 divided by y squared. Similarly, if the value of lambda is -1 after transformation, it becomes y to the power of -1, which is 1 divided by y, and so on. Note that you will use a different formula when you have the value of lambda as 0, wherein you will take natural log of the value y. Similarly, transform values are also shown on the screen. Click the Example button to know more. Let us look at an example of how data transformation is done using BoxCox. The difference between original data and the data transformed using BoxCox is shown on the screen. Figure 1 shows the original data plotted on a histogram. Here, you can see that this data is abnormal. In Figure 2, the Box and Cox procedure is applied on the original data, and it is transformed. You can see that the data in the second figure is more normal than Figure 1. Let us learn about process input and output variables in the following screen. Process improvement has a few prerequisites. Before a process can be improved, it must first be measured to assess the level of improvement required. The first step is to know the input variables and output variables, and check for any relationship. The SIPOC map and the cause and effect matrix are very helpful. There are many ways to measure the key process variables. Metrics such as the percent defective, operation costs, elapsed time, backlog quantity, and documentation errors can be used. Critical variables are best identified by the process owners. Once they are identified, cause and effect tools are used to establish the relationship between variables. A cause and effect matrix is shown on the screen. The key process input variables have been listed vertically, and the key process output variables horizontally. For each of the output variables, a prioritization number is assigned. Numbers which reflect the effect of each input variable on the output variable are entered in the matrix. The process output priority is multiplied with the input variables to arrive at the results for each input variable. The values are added to determine the results for each input variable. For process input variable 1, the output variables are 3, 4, and 7, with a prioritization value of 4, 7, and 11, respectively. Therefore, multiplying the output variables with their corresponding prioritization numbers and adding those gives 117, which is around 33% of the total effect. The process input variables' results are compared to each other to determine which input variable has the greatest effect on the output variables. Click the Cause and Effect Matrix Template button to view another template. A sample of the Cause-Effect Matrix, or CE matrix, is shown here. The CE matrix gives the correlation between input and output variables. In this screen, we will discuss the steps to update the CE matrix. The steps for updating the Cause and Effect matrix are: list the input variables vertically under the column Process Inputs. List the output variables horizontally under the numbers 1 to 15. These output variables are important from the customer's perspective. One can refer to either the QFD or the CTQ tree to know the key output variables. Rank the output variables based on customer priority. These numbers can also be taken from the QFD. The input variables with the highest score become the point of focus in the project. Another method to establish the cause-effect relation is the cause and effect diagram. This is explained in detail in the following screen. The cause and effect diagram is used to find the root cause and the potential solutions to a problem. A cause and effect diagram breaks down a problem into bite-sized pieces and also displays the possible causes in a graphic manner. It is also known as the fishbone, the 4M, or the Ishikawa diagram. It is commonly used to examine effects or problems to find out the possible causes and to indicate the possible areas to collect data. The steps involved in the cause and effect diagram are: all the possible causes of the problem or effect selected for analysis are brainstormed. The major causes are classified under the headings of materials, methods, machinery, and manpower. The cause and effect diagram is drawn, with the problem at the point of the central access line, and the causes on the diagram are written under the classifications chosen. The next screen illustrates the cause and effect diagram with the help of an example. The diagram shows the cause and effect diagram for the possible causes of solder defects on a reflow soldering line. This diagram helps in collecting data and discovering the root cause. During brainstorming, the group looked at all the major causes and then grouped them under the main headings. Under materials, causes like types of solder paste, components, and the components packaging used are considered. The major causes under methods are technology and preventive maintenance. Similarly, operator and schedule are placed under manpower, while tools and oven are grouped under machinery causes. The next screen will discuss another root cause analysis tool in detail. 5Y is one of the tools used to analyze the root cause of a problem. The responsibility of the root cause analysis lies with the 5Y analysis team. The technical experts have a great responsibility, as the conclusion will be drawn from the way the drill down of the symptoms is carried out. The 5 why is a very simple tool, as it poses the why question to every problem till the root cause is obtained. It is important to know that the 5 why tool does not restrict the interrogation to 5 questions. Why can be asked as many times as required, till the root cause for the problem is found. It can be used along with the cause and effect diagram. The following screen will explain the process of the 5 why technique. The process for the 5 why technique is: identify the problem and emphasize the problem statement. Arrange for a brainstorming session with the team, including subject matter experts, process owners, and team members. Explain the purpose and the problem statement. Analyze scenarios working backwards from the problem. Ask why for the answers obtained until the root cause is found. Normally, reasons like insufficient resources and time become the root causes. If the drill down in brainstorming is carried out in the right direction, it is often found that the root cause is related to the process. Therefore, the occurrence of a problem is often due to the process and not an individual or a team. In the next screen, we will understand the concept of the 5 why technique with the help of an example. The process for the 5 why technique is: identify the problem and emphasize the problem statement. Arrange for a brainstorming session with the team, including subject matter experts, process owners, and team members. Explain the purpose and the problem statement. Analyze scenarios working backwards from the problem. Ask why for the answers obtained until the root cause is found. Normally, reasons like insufficient resources and time become the root causes. If the drill down in brainstorming is carried out in the right direction, it is often found that the root cause is related to the process. Therefore, the occurrence of a problem is often due to the process and not an individual or a team. In the next screen, we will understand the concept of the 5 why technique with the help of an example. In this topic, we will discuss Lean tools in detail. Let us learn about Lean techniques in the following screen. The 8 Lean techniques are Kaizen, Bokayoke, 5S, Just-in-Time, Kanban, Jidoka, Tack Time, and Haijunka. Click each technique to know more. Kaizen, or continuous improvement, is the building block of all Lean production methods. Kaizen philosophy implies that all incremental changes routinely applied and sustained over a long period of time results in significant improvements. The second technique is Bokayoke. It is also known as mistake-proofing. It is good to do it right the first time, and even better to make it impossible to do it wrong the first time. The prompt received to save the Word document before closing it without saving is an example of Bokayoke. 5S is a set of 5 Japanese words, which translate to sort, set in order, shine, standardize, and sustain. This is a simple and yet powerful tool of Lean. The sort principle refers to sorting items according to a rule. The rule could be frequency of use or time of use. After sorting, the objects are set in order. The place for everything is defined, and everything is placed accordingly. Cleaning of the area refers to the shine principle. The 4th step requires formation and circulation of a set of written standards. The last step refers to sustaining the process by following the standards set earlier. 5S is useful as a framework to create and maintain the workplace. Just-in-time, or JIT, is another Lean technique. This technique philosophizes about producing the necessary units in the necessary quantity at the necessary time with the required quality. As an item is removed from a shelf of a supermart, the system confirms it and automatically sends a note for replenishment. This kind of technique can be used in an organization to prevent accumulation of inventory. The fifth technique is known as Kanban, which means signboard in Japanese. Kanban utilizes visual display cards to signal movement of material between the steps of a product process. This is one of the examples of visual control in Lean. The next technique is Jiduka. It means automation with human touch and is sometimes known as automation. Jiduka implements supervisory function in the production line and stops the process as soon as a defect is encountered. The process does not start again till the root cause of the defect is eliminated. Takt time is the maximum time in which the customer demands need to be met. For example, a customer needs 100 products, and the company has 420 minutes of available production time. Takt time equals time available divided by demand. In this case, the company has a maximum of 4.2 minutes per product. This will be the target for the production line. The final technique is Heijenka, which means production leveling and smoothing. It is a technique to reduce waste occurring due to fluctuating customer demand. Let us understand the concept of cycle time reduction in this screen. Cycle time reduction refers to the reduction in the time taken for a complete process. Implementing Lean techniques reduces cycle time and releases resources faster than any other method. Low cycle time increases productivity and throughput. Lean techniques release resources early, achieving more production with the same machinery. Internal and external waste is reduced, and the operational process is simplified with a decrease in product damage. All these factors help in satisfying the customer and staying ahead in competition. The following screen describes the concept of cycle time reduction through an example. The changes brought by implementing Lean techniques on an existing process are illustrated in the given diagram. Things to be noticed are number of operators used, work allocation to the operators, path or the movement in the process, and flow of the process. Notice the changes brought about by implementing Lean techniques on the old process. First, the path followed by the material in between the process is considerably reduced. This decreases the cycle time for the entire process. Second, the number of operators is reduced to 3 when compared to 5 in the old process. Operator 1 can now work on Process 1 and Process 4. Similarly, Operator 2 can work on Process 2 and Process 3. Hence, there is an increased productivity of the operators, and the remaining skilled operators can be used in some other process or system. The next screen will introduce the concept of Kaizen and Kaizen Blitz. Kaizen means good change in Japanese. Kaizen is a continuous improvement method to improve the functions of an organization. The improvements could be in process, productivity, quality, technology, and safety. It brings in small incremental changes to the process. Kaizen Blitz is known as Kaizen Event or Kaizen Workshop. If the event is tightly defined and the scope is evident for implementation, processes can be easily changed and improved. Teams could improve processes through creative problem-solving methods in structured workshops over a short timescale. The next screen will provide the differences between Kaizen and Kaizen Blitz. The differences between Kaizen and Kaizen Blitz are: Kaizen is a method that brings continuous improvement in the organization, while Kaizen Blitz is a workshop or an event that brings in change. Kaizen brings in small incremental changes in the organization. There are no major changes made within the processes. Kaizen Blitz is applied when a rapid solution is required. The Kaizen method follows a step-by-step process. It standardizes, measures, and compares the process with the requirement before improving it. Kaizen Blitz plans for the event, executes it, arrives at a solution, and follows it through. All the people of the organization are involved in Kaizen, whereas Kaizen Blitz is led by the top management and others are invited to participate. The decision-making lies with the upper management. In Kaizen, the process is standardized. and measurements are regularly collected and compared before the decision is taken. This relatively delays the process of decision-making. In Kaizen Blitz, decisions are taken soon, and the process change is wrapped in 3 to 5 days. Kaizen is a continuous improvement method, whereas the Kaizen Blitz is part of the improving process. Kaizen follows PDCA, in essence, plan, do, and check and act for the improvement process. Kaizen Blitz uses PDCA for execution, where the events are planned, conducted, decided, implemented, and followed up. The following screen will elaborate on the concepts of Kaizen and Kaizen Blitz through examples. Kaizen and Kaizen Blitz are practiced in many organizations across the world. The examples of Kaizen and Kaizen Blitz method are shown here. Click each tab to know more. The Toyota production system is known for Kaizen practices. In Toyota, if any issue arises in the production line, the line personnel cease all the production until the issue is resolved. Once the solution is implemented, the team resumes the production cycle. A wood window company in the state of Iowa, U.S., uses the Kaizen Blitz method to redesign their shop floor and replace expensive, non-flexible automation with low-cost, highly flexible cellular applications. Eliminating scraps, reorganizing work areas, and reducing inventory are some of the examples of quick implementation through Kaizen Blitz. Let us summarize what we have learned in this lesson. DOE are a series of planned and scientific experiments that test the impact of independent variables on dependent variables. During regression analysis of linear or nonlinear model, the value for y at level x is predicted. Residuals analysis helps you understand the accuracy of the analysis of linear or nonlinear model. BoxCox procedure is used for estimating the best transformation to normality within the family of power transformation. The 5Y tool is used to analyze the root cause of a problem. Cycle time reduction, Kaizen, and Kaizen Blitz help in improving processes. With this, we have come to the end of this lesson. The next lesson will focus on the control phase.